Welcome back. Up till now we've done quite a bit with the equation y is equal to ax plus e, and we've minimized the solution where over x y minus ax squared. We've explored several ways of doing this and ways of dealing with the growth of amplification of the error, if that exists. But let's look at a simple problem as an example. And that problem is assume that we have data points and we want to do a line fit to those data points. Maybe something like that. What exactly are we solving when we minimize y minus ax? In fact, what is y and what is a in this situation? So in here we have our yi's, and over here we might have our ti's, our time. X is what we're trying to find. X is equal to slope plus y-intercept. So that's our unknown. The actual samples and time are known. So then A would be equal to T1 and 1, T2, 1, so on up to Tn. And 1. And therefore, y1, y2 up to yn would be equal to T1, 1, T2, 1 to Tn1 times slope plus y-intercept plus error in this term. So each, and this would be a vector, so we would get E1, E2 up to En. As a result, yi is equal to mti plus b plus ei. So that defines the line. And we're trying to find the m and the b such that the squared error is minimized. So what is that squared error? Well, the squared error is the y offset. So we are minimizing these distances right here. Minimizing the error on the y-axis in this particular example. Well, you might recall that there was a time when we talked about maybe minimizing the distance to a line. It was a slightly different context. But sometimes, try that in a different color. Sometimes we may want to minimize differently. That is, maybe minimize the distance to the line. Now we already know how to do this. If we were given a line, we know that we can minimize the distance to the line by finding the projection onto that line, and such that the error, this what's in red, is orthogonal to the line. So we just want little orthogonal things there, and that minimizes the distance to the line. So we know how to do that, but that's not actually the question in this case. What we have here is we have the points, but we don't yet have the line. Once we have the line, we know how to solve the problem, but we don't have the line. We're trying to find the line that minimizes that total error. So this looks like an optimization problem of some kind or other. But first, let's look at how we actually visualize this. We have our TIs and our YIs. So if we were to zoom in at say this point right here. And take a look at that. We have our line. So it looks like I've just fallen asleep on the job, but sometimes it stops scrolling, and I'm not sure what causes that. So we have a view of our line here. There we go. And we have our error points. One there and one there. We're trying to find this. So the first thing you note is that there's assumed to be some error on the y-axis. But the other thing to note is that there's also error on the t-axis in this particular case. So where is t? T is our sample points. So this is assuming we have errors in both directions. So we're going to simplify our approach here, and we're going to assume that we have, in this particular example, we'll get rid of the b term, and let's just look at the slope and see what happens. But first we can set up the problem, which does work in general. So what we have can best be understood in terms of what we've been looking at before. In this first example, we are trying to minimize minimizing delta y. In other words, we want to find the smallest offset from y such that this equation is solvable. Well, back to this case, we are now going to find the smallest offset from y and the smallest offset from A. So that's in X. So we're finding the smallest ones so that we have an exact solution to that equation. So how do we do this? We're effectively going to minimize over delta A, delta Y, and X the Frobenius norm squared of our delta A and our delta Y, giving them equal weight right now, subject to Y plus delta Y equals A plus delta A times X, where the Frobenius norm is squared is the sum of each individual element squared. So, how do we go about solving this? This is going to take a few steps, so we will start undertaking this in the next lecture.